Good morning. By the end of this video, you are going to derive and use all 5 uniform equations of motion. You're going to be able to practice problems using these equations, and hopefully, if I give you a problem, you will be able to discern which equation to use in what situation. So equation number 3. Equation number 3 is an equation we can use if we do not know the overall displacement of an object. In order to solve for equation number 3, we're going to use equation number 2 and the fact that change in velocity is final velocity minus initial velocity. So we know this is equation number 2, and we know that delta V is final velocity minus initial velocity. So now what I'm going to do is I'm going to substitute in VF minus VI into delta V in equation number 2. That's going to leave me with acceleration equals final velocity minus initial velocity divided by change in time. I can put the acceleration over a 1 and cross multiply. And that's going to leave me with acceleration times the change in time equals VF minus VI. My last step is to isolate final velocity. This equation is very useful if I want to find the final velocity of an object, if I know its initial velocity, acceleration, and the time it traveled. So adding VI to both sides, I'm going to be left with equation number 3. Final velocity is equal to acceleration times the change in time plus the initial velocity. Notice that this equation is in slope-intercept form. What I mean by slope-intercept form is y equals mx plus b. Your independent variable would be your final velocity. Your slope would be the acceleration, which, thinking back to a velocity time graph, we can find the slope of a velocity time graph to get the acceleration. Your independent variable is your time, and your initial velocity is your y-intercept. Write that equation down, label it third equation of motion, highlight it, and after you've done so, move on to the next slide. So we're going to use the third equation of motion to solve this example problem. A car starts from rest, which means the initial velocity is 0, and travels 5.0 seconds with a constant acceleration of negative 1.5 meters per second squared. What is the final velocity of the car? So I'm solving for VF. VF is already isolated on the left side of the equation. VI is 0 because it's starting at rest. My initial acceleration is negative 1.5 meters per second squared. And last but not least, my time is 5 seconds. So going off screen for a moment to solve this out, I have negative 7.5 meters per second as my final velocity. Sig figs, there are 2 because time and acceleration both have 2 sig figs. The final velocity is negative, the acceleration is negative, so I can make the claim that this car is moving at a rate of negative 1.5 meters per second square, which is its acceleration, in the negative direction. And I know it's negative because the acceleration and final velocity are both negative. Equation number 4. What if we don't know final velocity? If we don't know or can't use or solve for final velocity, we are going to create an equation which leaves it out. All of these equations are derivations of the previous ones. So for this particular equation, we are going to use equation number 2 and equation number 3. In equation number 2, you've got 1/2 VF plus VI times delta T. And for equation number 3 is the one we just derived, final velocity equals initial velocity plus acceleration times change in time. So what we are going to do for this particular equation is recognize that I can substitute VI plus AT into this equation for VF. So I will say my change in displacement equals 1/2 VI plus VI plus AT all times time again. And I know sometimes my pluses look like my T's, so you just have to put up with me. And that's a plus. So all I've done here is substituted in VI plus AT in for VF. And then I'm going to simplify a bit. I'm going to say that this is equal to 1/2 times 2 VI plus AT all times T. Notice I left out the delta here, and that's just for simplification of deriving the equation. I can leave out the delta because that just means change in time. Change in time and time are usually the same thing. And now I'm going to distribute the 1/2. So I'm going to have 1/2 times 2 VI and 1/2 times AT. So that's going to get me 1/2 times 2 is 1. So I have 1 VI plus, and I will put this in parentheses, 1/2 AT all times T. And then what I'm going to do is I'm going to distribute the T. And when I distribute the T, I'm going to end up with my final equation. I'm going to have VIT plus 1/2 AT squared, which is going to be your change in displacement. I can also write it as we see it on the wall in my classroom or in your textbook as 1/2 AT squared plus VIT. This is equation number 4. Make a box around it, like I'm going to do right now, and label it equation number 4. And then when you are ready, move on to the example problem. Same car, different equation, different thing to ask. A car from rest travels 5.0 seconds with a constant acceleration of negative 1.5 meters per second squared. How far this time did the car travel? So we're going to use equation number 4. And that's going to be 1/2 AT squared plus VIT. Filling in the blanks. Acceleration is negative 1.5 meters per second squared. And then only time gets squared in this equation. So it's only going to be the 5 that is squared. Plus 0 times 5, which is a term that's just going to get to cancel out. We like it when the object is initially at rest because this term, fortunately, just goes away. So now I'm going to be left with half times negative 1.5 times essentially 25. And my answer ends up being negative 18.75. And since we're doing displacement, the displacement will be in meters. Sig figs, got to round to 2 again. That's going to be negative. And then I look after the 8, that's a 7. That brings the 8 up to a 9. So negative 19 meters. Going backwards, which correlates to the equation number 3 problem, which says that the velocity was going into the negative displacement direction as well. I'm going to pause the video here, and then the next video I'm going to attach is the magical equation number 5. And if you'd like to go ahead and solve the problems that go with equation 3 and 4, you can do so now. They are starting on page 54 in your text. See you in the next video.